Okay, we're going to take a shot at trying this web recording of the lecture uh, so that you guys can get out of Dodge for spring break and generally see how this might go. Um, what I'm going to do is real briefly just remind you where we were last time, and I'm going to go through some details of how one can relate some of the equations and developments we did to the actual concept of determining the number of stages for the absorption of acetone in an absorber using the basic concepts of multi-stage operations. So if you look here, this slide is just a scan from last lecture, where what our goal here was to develop an equation for an operating line. And in this particular problem that we had developed, so I'm going to go ahead and I'll just take that and I'm going to just put it into a problem statement here and snip that. So we have our example problem. This is taken from noted here Giancopoulos. It's a very simple gas absorption problem, and so that being the case, actually, I'm gonna. That's what I need to do. There we go. Take a new snip. I'm just going to snip this example problem here, and I'll throw it over into the spreadsheet. I'm going to give you the spreadsheet then at the end. So the problem, as it's stated, is a dilute acetone stream that's being absorbed with water, and in the process, what I've just done in advance here is what we had gone over last time in class, and that is we used just the overall mass balance to go ahead and to determine essentially what was given in the problem statement, just total gas flows 30 moles per hour. Total liquid flow for water was 90 moles an hour. Pure water was being used, so the mole fraction was 0, and we were given the dirty gas composition for the acetone. Doing an overall mass balance gives you the ability to do the calculation. The changes in the gas stream, because of course you're taking acetone out, but since this is such a low concentration, you'll see that it really doesn't change much, and that's also true for the liquid stream. This provides for a pretty substantial simplification with regard to the operating one, which I'll go ahead and I'll just grab that here too as well. So so we need to get that out of our way in order to do that. Cool. And so this equation for the operating line, what it does is it lets you predict essentially the next mass balance to a stage, which would be somewhat difficult if you have a variation in that quantity, because if you take a look at this, it's basically y equals mx plus b, right? It's y equals mx plus b, where the slope is defined by this liquid to vapor ratio, and b is also varies slightly in relation to the vapor phase change as well. In this case, since these numbers do not change very much, then what we have for this is basically the value for the slope will be taken directly as the ratio of the gas flow, and I'm just going to take this to be roughly 30 over 90. I could do it, I suppose, B1 over Ln as well, give you an idea what they look like, the difference, and they're not that much. And so if I was to do that same number and calculate it based on the outlet values here, oops, and the L divided by B, should be the same here. And then you can see 3 versus 3.03. Not a large number in terms of what we're working with here. And the value of the intercept is also pretty straightforward. B would equal basically y1 y1 b1, so that would be here times the vapor coming out. Oops. Let's see, undo that. Undo it for me or not. So B will be equal to y1 times v1 minus the acetone that would be coming in, which in this particular case is 0. And that quantity then will be divided by the vapor. This is n plus 1, so we'll just go ahead and grab that as well. So that gives us now our operating line, and just so that this is sort of a little more obvious to you, looking what we were thinking about conceptually here, that we have an equilibrium line, which that's just a given in this problem. We have the operating line. And ultimately, our goal is to actually step off the things. But what I really wanted to do in this lecture is show you that this you can literally calculate this in the spreadsheet directly, as opposed to doing it all completely graphically. It's also pretty informative to do that, since you literally go from stage to stage, equilibrium to operating line, and reinforce your understanding of what's happening for the staged operation. So that being said, I wanted to just expand this out. I'm just going to simply graph it. It's not rocket science here, but let's say we have X, and then we'll have Y. Oops, this would be the Y, where this would be the equilibrium line, and we'll just call this one the operating line. We know our X values are going to go from 0 to 0.003, so we'll just simply take that from 0.001 and we'll take it on down to 0.003, a little bit more than that, so 3, a little bit. Okay, so those will be our X values. You'll notice in the this problem statement as well, there is also a equilibrium line given, and in fact, I'm just going to move these down just a tad so I can put that in. And the equilibrium line is simply stated. If you read up here, it's y equals 2.53x. Okay, y conveniently given in this particular problem, so we have to do unit conversions. X. So with that being the case, I'm just going to create a reference cell to make this easier to do, and I can then take the value of the slope. I'm going to hit F4 here to make it an absolute reference cell, and then multiply that times the equilibrium. Functionally, this number incorporates in it Henry's law, basically. This is acetone into water, and that gives rise to a certain solubility, and that solubility expressed at the pressure and temperature of the system is given. So there you go. So that gives us our equilibrium line. The operating line is essentially almost as easy to deal with. So we have it's here, it's y equals m. We'll use this one to be conservative, and multiply that times the density. So I'm just simply plugging in y equals mx plus b. This is the operating line. This will be a little more obvious when I just go ahead and make a graph of it here. So first, let me just drag this down, finish off this. Okay. So there. Now we can make a graph here. So that being the case, I'm going to go ahead and make a line chart, and there you go. This will give us our equilibrium and operating line. And I'm just going to fatten that up just a little bit. So we're going to draw a few lines on it. So functionally, I'm going to not change the size of that anymore, because now we can kind of look at it and get a feeling of where we're headed. This point right here, which represents an x value of 0. And this operating line here, that is basically at the top of the column. And so what that does is that gives us the place where we would normally be doing our stepping, but we need to know where we're stepping to. And that's given by the outlet composition. So I'm going to go ahead and see if this isn't too annoying to try to do, and just indicate that right here, there we go. This line right here that I just put in is the target. I'm sorry, no, that's the supply composition. And down at the bottom right here is where it will be coming out. So that being said, we can go ahead at this point and go ahead and copy that and sort of like put some little hashes on here that would be equivalent to our sort of stepping off things here. And then what I'm going to do is I'm actually going to calculate those points using the equilibrium and operating curve in this example. So let's see if it will let me color that line. Let's make it, let's think of it from heading across, that we're finding the equilibrium. So if I were to place this here, this is our operating point leaving the reactor. This is the gas that's been cleaned. And this is what composition of liquid would be in equilibrium with that. So as I had sort of indicated before, we would need to then, let's see, insert this line again. Lock in there. There we go. So I'll let blue be the case. So here, if I were to take this on up to the operating curve, that would give me 1, and then I can just build these out now, where I would go ahead and sort of step off, if you will, stages from this thing. So maybe I'm not real keen on this as my line. I'm going to go ahead and put a solid line in there so that's something to work with, and one there as well. A little easier to see where I'm crossing. And there you go. That'll make my way. I can kind of sort of step my way up here. There's the ones right about there. And step my way over. And what I got is back here. D. And that probably wouldn't hurt me to just increase the size of that just a little bit. So whoa, okay. There we go. And yeah, there we go. Ahead. And graphically, I'll call that Control D here. And you can see we're getting, what we're doing is working our way backwards. This here is functionally, you can think of it as the top of the column. So I'll actually put it in here, and I'll put that in here, the text box. Right, this is the top. And because this is where the water is coming in at clean water, and this is where the clean gas is actually going out. And yet we know what we have up here. This is going to be the bottom. Because this is where the gas is going to be coming in, and the dirty water is going to be exiting. So far, starting from here, we have 1, 2, 3, 4, 5, but it still isn't quite enough to get us where we need to be. So we're going to need to grab another one here. D. And throw that there. Let's see, 1, 2, 3, 4, 5. And let's see, we probably cheated just a tad here. I'm just sort of looking at making this a little more consistent with the example I had. This one's a little high. I can see my lines. This one's definitely over a little too far. That's the intersection is there, and this one a little bit there. Yeah, definitely nudge that one over a little too far. This one comes up. So this one I was going to intersect this one here. Will come back. I'm matching the points where these steps actually cross, and this one's here. This is down a tad. This one's here. There we go. That's a little more realistic. So if I needed essentially one more, which I will, I mean, the actual numbers for this, insert a text box, call this one 1. I'll make the text box color green. And this one represents essentially stage 1 here. And go way up to is this is the next stage, where again, think of this as the exiting gas. That exiting gas is going to be equilibrium with the liquid that is on that stage, and then that liquid composition, the equilibrium, is defined by the mass balance to head to the next stage. So each one of these then represents another additional stage. And so here's 3, and there's 4, and there's 5. But it's not quite enough. And in fact, the way that this is handled is that, well, I mean, you can have a fraction of a stage in theory, right? But you can't really buy half a stage. So you would actually make it bigger. I think there's another concept we'll be talking about later, that the stages aren't necessarily 100% efficient. And so sometimes there's an efficiency factor as well, so that you would actually add additional stages to accommodate the fact that it would be not quite 100% equilibrium stage. Okay, so I'm going to go ahead and just hold down the control key so I can use a little less cumbersome. And let's see. So this is the graphical approach. You know, we briefly talked about it last time, but you can kind of think of it as literally starting at the top of the column, knowing what our target is for cleaning the gas. So this is, again, clean gas here, clean water going into the column, countercurrent extraction, and then stepping off each of the stages between these 2 lines. So you go from equilibrium to operating to equilibrium to operating, and each one of those represents a stage. In this particular one, I think they graphically estimated it at 5.2 stages. I don't think it's that critical at this point to nail that down. But what I did want to do is then look at this a little more analytically from an actual calculation. So to do that, we can actually calculate these points rather than simply getting them graphically. Control, let's see, I just made a convenient little multi-stage absorber here, which I can paste in. So here we now have our liquid stream. I go ahead and I think a little bit bigger. And think of this in terms of a stage-by-stage walk. Okay, so if I wanted to calculate what this is, this represents Y1, and so that Y1 is therefore in equilibrium with this X1 right here. So really how I might do this, but I'm going to go ahead and say, well, this one here, oops, is in equilibrium with that one down there. Okay, so that being the case, we'll make it, we'll make it red. This is literally walking from this point right here that you see, that I'm circling here, right over to that line. Well, how would I calculate that? Well, let's go ahead and we'll call this stage, well, I'll go ahead and I'll calculate it just based on equilibrium, right? This number here will be equal to, I want the x value, so I simply take the y value there and I divide it by the equilibrium the relationship. This is a phase relationship, Henry's law in this case. Let's see, what would be the best way to do this? Well, I guess I can go ahead and since we know what y1 is, it's up here. I can take this number and I can divide it by that number, and there's my mole fraction of acetone in that stage. From that, I can come over here then, and I can then calculate. I just calculated this point right here. So if I were to take a circle, let's say, and not fill it with anything, and let's see, so this point right here corresponds to this one right here. So I'm going to go ahead and make a connection between there to here. So then from that particular point there, I can go ahead and I can calculate based on the operating line. Since I now know x1, okay, this is well, it's not as bad as I thought it might be, but this is x1. X1 is this point right here. So I can grab that point. I can also do that so it doesn't. Yeah, I'll do that. So now that I have x1, I can put x1 into the operating line, which is this equation here, and calculate the next point on the other side. Okay, I'm not exactly sure where this had closed out. Seems to have crashed at the actual recording here before. So I'm just going to actually sort of reiterate just a few things here that hopefully we can stitch back together. Remember, this is the multi-stage absorber. We know what we want. This is the clean gas coming out, and so that clean gas coming out is literally a specification. Okay, so that's what we want. That's actually up here, so that's y1, and that's what gave rise to this number here, and that number, which corresponds to this location, if you will. This is the y-x diagram. This axis is y, this axis is x. So clean water was coming in, and at the top of stage 1, which is where we are right here, corresponds to this particular data point here. That data point is then used to calculate across to x1, which is determined by equilibrium. And if you click on this, what you'll see, all I did is I just simply used the equilibrium line to calculate from y1 divided by functionally the phase partitioning, in this case Henry's law, solubility into water, and that gave us our first stage exit in the liquid phase. So clean water coming in here, and the initial low level of acetone that has been absorbed over here. This number here then represents, if you take a look back over to where we calculate that number to here, that represents the individual number that is calculated from the operating line. So this green circle here represents the going from here over to what's leaving this as constrained by the mass balance. That'll be y2. And that number is calculated based on the formula of the operating line here, which is basically the slope and the intercept associated with that operating line. You can then see that as you can just simply walk down here as you can want to, and from each of these, when you're calculating across now to the equilibrium, that is exiting stage 2 of the liquid, which would be right here, that will be simply that y value divided by the equilibrium constant as well. And successively, then you can calculate. I'm not sure if this is a good idea or not. Let's see. Apparently not. I was going to try to control. No, not a good idea. I was going to calculate that again from the x values, so it'll basically be equal to the slope times the x value that is in the operating line 4, and then add in the intercept, and there you go. Walking your way down from stage to stage is literally the process of going from that point to this point. That's going from here to here. From there, that's going across and down and across and down. From the vapor phase that is leaving based on mass balance, and the water phase, the acetone, that is basically calculated from the equilibrium curve. And now, as I do this, what you'll see is the interesting aspect of this is that I know what I want. I need to figure out how many of these stages that I need to actually get to the point where I am accomplishing that output goal based on the input, because the input is down here somewhere. And so as I now get the operating here, I'm slope times the x value plus that, and that's once again it's just the equilibrium. That's the operating curve. I can calculate now x4 from equilibrium very easily, divided by slope. And if I don't get confused as I make my way down through here, this would be m times x plus b. That's the operating curve. And you can see it, I keep getting higher inlet compositions. So right now we're at 0.007. The problem is that I need this to be here. This is our kind of our holy grail target, is defined by our dirty gas composition. And so I'm going to go ahead and here. This one is, oops, that's kind of annoying. Try to get that without it getting in my way. And I'll make that heavy so you can really see it. That this really represents the inlet target goal. And so we're looking for this number to be one of these numbers here. It's going to have to be, it can be higher. The inlet can be higher, because what it's saying is this column, if it had an inlet composition that is this or lower, this number here, 0.007 or lower, it would achieve the outlet goal of the level of extraction of the acetone. But clearly that's not enough. And so we're going to have to go ahead and have another stage here, add equilibrium with that number. Oh, there, oops. I didn't like that. Problem with mixing this, divided by the equilibrium again. And then we come back to the operating line as well. And that'll be m times the stage equilibrium plus the intercept. Now you can see we're at 0.099. That's almost enough, but it's not enough. Okay, so we need this to be 0.01. And so it turns out that you can see that 5 stages is almost enough, just as we saw over here, where we had 1, 2, 3, 4, and 5 almost got us what we needed, but not quite enough. And so if we go to the next stage, of course, it's going to be a little overkill, but that's good. Okay, so here, let me set this up in equilibrium with that stage. And when I calculate this, of course, I'm going to expect this to be substantially higher than our target, because we were almost there in the last stage. And so here we'll just simply then take m equals sneak underneath that one, m times x plus b for operating. So we're calculating across and up here somewhere. So it's going to be quite a bit higher. Plus b. And yeah, okay, we'll assume that's right. And you can see that, yes, this is substantially greater than this. So 5 plus some additional stage is more than adequate. And so we've accomplished this now by literally, instead of just walking this off graphically, of trying to calculate it. We're making the same assumptions, because note that if we didn't have the simplicity of this assumption that this L over V was constant, we would need to know the slope on each one of these. So this line, this would be a curving line. But note that we don't know the value of this vapor or the liquid if there's a large amount of that transferring from, for instance, if let's say the water is vaporizing and going into this stream, then what's coming out here is going to be a larger number. And so L over V will then be changing with each stage. And we can't know that until we know how many stages we have, because the number of stages in practice is a real number, not a fractional number, and we're walking towards it. But we're walking towards it assuming we know that the L over V is constant. If we did not know that was constant, this would be quite iterative in nature. We need a better way, if you will, to find the operating curve in terms of calculating its value. And that's something that is going to be literally the critical sort of next part of this course. Well, for different unit operations, like for distillation and things like that, getting that operating curve is the hard part. From there, it's stepping it off, whether it be graphically or whether it be from just a straight up calculation. That ultimately becomes a difficult part. I'm going to go ahead here now, and I had actually done a piece of this before, so I'm going to go ahead and grab this. Let's see, and I think I can do this without it getting too excited. Let's see. And this is just a more compact version, if you will, of this, where I've literally set up the, okay, see, I can't really do that, not here. I'm not gonna do that. Maybe this is just a mess. This was doing the calculations without making the pictures, and so I literally set up, and here is Y1 that's known. This is Y2 calculated from equilibrium. Here is, well, actually, we'll go step to the next one. So here I'm doing it in the reverse. I'm using the known to get the equilibrium, then going through the operating curve, and so forth. It's a little confusing this way because of the ins and outs. So if I say this is the stage in here, this is in on stage 1, and that would be the out on stage 2. So when I get the whole way down here, I'm actually looking to have a target of 0.01, which you can see is between these two here. And this number here is n plus 1. And so this is actually stage 5 plus a little bit, not stage 6, because of the nature of there's a stage there. And on one hand, I'm looking at what's going in on the stage. In this case, it's out, and in is has n plus 1. So stage 1 has y2 feeding it. Stage 2 has y3 and so forth. And so you can see that y6, even though it is being calculated for stage 6 based on the operating line, is actually the feed for stage 5. So you only physically need that because that feed is our dirty gas feed. We don't need to have a stage feeding it if it's greater than that value. So that is, really what I had wanted to do. I wanted to make sure that I, went through an example, not just simply a simplistic one of sort of step-by-step staging, but also showing then the direct relationships for the equilibrium and so forth. And I wanted to sort of, one last comment I'll put in here is that if you think about this, I'll start with this next time. This is actually not a realistic picture, if you will, of a gas absorption. That's usually done in a packed bed where you're just running water over beads or something. And so these stages are theoretical equilibrium stages. And what happens is you calculate the number of theoretical equilibrium, in this case 5.2, I think is the number in the book. And the staging then gives rise to, I'm sorry, I was a little distracted there, a theoretical for 5 stages, and then you get an efficiency that works in. In other words, this is not a stirred tank here that you would do gas absorption, and from stirred tank to stirred tank, you would actually do it from the you would actually do that staged equilibrium based on the feeding and efficiency. So it's at 5 and you say 80% efficient, so then you divide by 0.8, it would give you an additional number. It's a convenient way of thinking about the stage due to the fact that the gas streams don't change much in absorption. But the actual physical column, or absorption column, would just simply be a packed bed with a sprayer on top. So that is what I have provided as a lecture, and I will be uploading this spreadsheet as well. But what I encourage you to do is not just simply look at what I've done, but to clear out some of the elements of this and go from there.